As is well known, experience shows that compressed rods lose stability earlier than Euler's theory predicts. There are several reasons for this. Of all these causes, only initial geometric imperfections can apparently be described numerically. If the rod's geometry deviates from a straight line, then even under central compression, a moment stress state arises. And if the stress in one of the fibers reaches the yield point, lateral buckling begins, which can quickly progress to a loss of stability in the elastic plastic state. The solution to this problem is based on the solution to the problem of longitudinal bending of a hinged rod with an initial deflection. If we take the form of the imperfection as a sinusoid, find the expression for the moment at the middle of the span, add the stress from bending with the stress from longitudinal compression, and equate their sum to the yield strength Ry, then as a result we obtain the well-known formula. Here Ny is the longitudinal compressive force at which the design stress Ry will appear in one of the rod fibers. A is the area of the element, and the coefficient phi is calculated using the formula. That is, the check consists of making sure that the compressive force acting in the rod is less than Ny. This formula is written in Eurocode in this form. The same formula is used in all national standards, albeit with some ritualistic frills. The difference between the standards lies solely in the method of normalizing the reduced eccentricity of roughness. But what if the boundary conditions differ from the hinges at both ends? It can be shown quite correctly that if the shape of the initial imperfection is proportional to the buckling shape of the rod under the given boundary conditions, then the coefficient phi will be calculated using exactly the same formula, only with the replacement of the physical length of the rod with the buckling length, the distance between the inflection points on the buckling mode curve. That is, checking the local stability of rods using the buckling length method assumes that the initial imperfection shape is proportional to the buckling mode of the rod under the corresponding boundary conditions. More precisely, it is sufficient that the second derivative of the initial imperfection shape be proportional to the second derivative of the buckling mode. The question arises, why should the shape of the imperfection be chosen proportional to the shape of the buckling mode? Perhaps this is the very worst form of imperfection that provides the greatest bending moment in the rod? Or is it possible to select a more unfavorable form of unevenness that produces a greater bending moment, all other things being equal? It turns out it is possible. For example, the moment at the midspan of a hinged beam with a sinusoidal imperfection is described by the expression. And the moment of the same beam with a parabolic imperfection is described by the following expression. The figure shows the graph the ratio of the moment from a parabola to the moment from a sinusoid depending on the compressive force. As can be seen, this ratio is greater than unity across the entire range of force variation. That is, a parabolic imperfection with the same rise will always give a higher torque value, although not significantly different. And this is far from the limit. Nevertheless, we'll leave this question open for now. Why, nevertheless, is the method for testing the local stability of rods based on the shape of the initial imperfection, proportional to the shape buckling mode? Firstly, intuitively, it seems like a good choice. But most importantly, it is precisely because of this choice that the extreme bending moment can be represented as a closed-form formula. And it is precisely because of this choice that we owe such a concise formula for calculating the coefficient phi. With any other choice of initial imperfection shape, nothing similar would have been possible. Let's return to calculating the buckling lengths. We know well how to calculate the buckling lengths if kinematic boundary conditions are specified at the ends of the rod, a hinge, a free end, a fixing, and a slider. To do this, we need to find the critical force value and using the well-known formula, find the buckling length of the rod, here mu. The buckling length coefficient is the ratio of the buckling length of the rod to its physical length. But what if the rod is an element of a complex structure? Consider the structure shown in figure. Let us want to find the buckling length of the rod attached to nodes R and S. To do this, it is necessary to construct a stiffness matrix of the system, reduced to nodes R and S. Denote this matrix as SRS. Next, we exclude from this matrix the unit reactions of the element Rs itself, and instead of them we add the reactions of this same element as functions of the critical parameter alpha. Let us denote the proper matrix of unit reactions of the tested rod Sm of alpha. Thus, the problem of determining the calculated length of the element Rs will be reduced to solving the equation relative to the parameter alpha. Here Sm of alpha 0L is the matrix of unit reactions of the element Rs at the current value of the longitudinal force N0. The main difficulty of the described procedure is the construction of the stiffness matrix of the structure reduced to the nodes fastening the test rod, matrix SRS. We need to somehow move from the main system shown on the left to the main system shown in the picture on the right. We are well aware of the physical interpretation of the Gaussian elimination procedure. Eliminating the ith variable is equivalent to dropping the restriction from the ith degree of freedom of the system. That is, we need to place the rows corresponding to the nodes of the tested rod at the end of the system's stiffness matrix and process them with all the rows above them. In other words, we essentially need to perform a forward sweep through the entire system matrix. And this procedure will need to be performed to find the buckling length of each rod. Clearly, if our structure consists of hundreds or thousands of rods, this procedure becomes prohibitive. Let's assume that we have somehow managed to construct a matrix that is the inverse of the original system stiffness matrix, the flexibility matrix. We will denote this matrix by the letter F. Note that the physical meaning of the coefficients of this matrix is the displacement in direction of the ith degrees of freedom from a unit generalized force applied in the direction of jth degrees of freedom. The flexibility matrix has one remarkable property. If we select blocks in it corresponding to the deformations of individual nodes, form a general truncated matrix from these blocks, and calculate its inverse matrix, the resulting matrix is nothing other than the stiffness matrix of the entire system, reduced to the selected nodes. Indeed, we introduce a force vector whose components for all degrees of freedom, except those that correspond to the selected nodes, are equal to 0, the first column of force vectors. The components corresponding to the selected degrees of freedom related to the nodes R and S. We will select in such a way that, being multiplied by the flexibility matrix for the first degree of freedom related to the selected group of nodes, we obtain a generalized displacement value equal to 1, and for all the others, 0. First column of the matrix I. Obviously, the force vector selected in this way is nothing more than the reactions and the restrictions imposed on the nodes R and S from a single displacement of the first of these restrictions. Provided that all other nodes are free, the force vector is defined in such a way that the reactions in these restrictions are 0. Continuing this procedure for all other restrictions of the truncated system, we arrive at an obvious equality. Where FRS, a truncated flexibility matrix formed from the cells of the general flexibility matrix of the system related to the selected pair of nodes. SRS, the stiffness matrix of the entire system, reduced to the selected nodes, I, identity matrix. Hence, the desired stiffness matrix of the system, reduced to the selected nodes, is determined by the equality. Thus, in the presence of the flexibility matrix of the entire system, it is possible to select blocks in it associated with a specific element and form a stiffness matrix reduced to the selected nodes. The next step is to subtract from the reduced stiffness matrix SRS the unit reactions of the tested element under the effective value of the longitudinal force, and substituting in its place the unit reactions matrix of the same element, but this time depending on the parameter alpha, the eigenvalue of the boundary value problem. But here, everything is being hampered to the flexibility matrix of the entire system F itself. First, the system's flexibility matrix is completely filled, which causes problems with storing the matrix. Second, even taking into account the symmetry of the flexibility matrix, the cost of generating it for our computational schemes may be incommensurate with the capabilities of modern consumer computers. Nevertheless, the specifics of the task at hand make it possible to solve this problem with very little computational effort. First, note that, despite the fact that the flexibility matrix is completely filled, all matrix blocks of interest will be located within the same band structure as the original stiffness matrix. Second, since the flexibility matrix, like the stiffness matrix, is symmetrical, it is sufficient to form, for example, only the elements lying below or above the main diagonal. Since the stiffness and flexibility matrices are mutually inverse matrices, then formally the procedure for constructing the flexibility matrix is reduced to solving a system of equations, where S and F are the stiffness and flexibility matrices of the entire system, I, identity matrix. Let's recall how we solve the displacement method problem if we have several columns of right-hand members. First, we do a forward sweep through the stiffness matrix. Then we do a forward sweep through the right-hand side matrix. And after that, a reverse sweep through the right-hand sides. As a result, in place of the right-hand sides, we have vectors of unknowns. To calculate the flexibility matrix F, we will consider equation as a system of n equations with n columns of right-hand members. The ith column of the right-hand sides in the initial state contains a 1 in the ith position. All other elements of the ith column in the initial state contain zeros. We divide the procedure for solving this equation into 3 stages. The first is the reduction of the stiffness matrix S to the triangular form by the Gauss method. The second is the direct Gaussian sweep on the matrix of right-hand sides. Third, reverse Gaussian sweep on matrix I. The figure on the left shows the system stiffness matrix, reduced to a triangular form by a direct sweep according to Gauss. On the right, the process transformation of the identity matrix into a flexibility matrix. As a result of a forward sweep through the right-hand side matrix, the entire triangle below the main diagonal will be filled, while the zeros above the main diagonal and the ones on the main diagonal will remain in their original state. Let's consider at the reverse sweep procedure using an example JTH column of the formed flexibility matrix. Let, as a result of the reverse sweep procedure, all elements of the JTH column lying below the main diagonal were calculated. To find the diagonal element indicated by the question mark sign, it is necessary to multiply the previously calculated elements of the JTH column AC of the formed flexibility matrix by the elements JTH row AC of the stiffness matrix. Then subtract the resulting sum from unity element A of matrix located on the right, and divide the result by the diagonal element of the stiffness matrix, element A of the matrix located on the left. Obviously, the values of the previously calculated elements of the JTH column lying below the point B. located on the boundary of the band structure of the flexibility matrix will not affect the value of the diagonal element A of the flexibility matrices, since they will all be multiplied by zeros of JTH rho of the stiffness matrix located outside the width of the band. Similarly, when forming all elements of JTH column located above the main diagonal, the elements located below element B will also not affect their values in any way for the same reason. This means that there is no need to either calculate or store the flexibility matrix elements located outside the band width. Thus, if a way can be found to calculate the elements of the JTH column of the flexibility matrix located within the width of the band below the diagonal element, without first calculating the elements located outside the band, then the problem of forming the flexibility matrix will be solved. The following algorithm solves this problem. We perform the first step of the algorithm, reducing the matrix S to a triangular form using the Gauss procedure. The second step is a forward sweep of the right-hand side matrix. But, since the last column of this matrix remains unchanged after the forward sweep, remind that the last nth column of the identity matrix contains the only non-zero element, the unit in the cell nn. Then, by omitting the forward sweep, we can immediately perform a reverse sweep along this column. And, since the elements of the flexibility matrix beyond the width of the band are of no interest to us, the reverse sweep can be performed not over the entire height of the matrix, but only within the width of the band, the section AB. Since the flexibility matrix is symmetric, we reflect the elements of column AB onto row AB prime. Let's move on to the n-first column of the flexibility matrix. Since the subdiagonal element in this column is already known, we immediately perform the reverse sweep, starting from the diagonal element and also within the width of the band. We reflect the calculated elements of the n-first column onto the n-first row. Continuing this procedure, we sequentially fill the band structure of the flexibility matrix. The algorithm can be constructed in such a way that it is not necessary to fill the subdiagonal part of the flexibility matrix. Therefore, the required external memory for storing the requested data of the matrix F no more than that needed to store the band structure of the system stiffness matrix. It can be shown that the number of operations for forming the band of the inverse matrix is approximately 2 times greater than the number of operations for the Gaussian elimination procedure for converting the band structure of the stiffness matrix to a triangular form, which is much more efficient than forming the system stiffness matrix and processing it according to Gaussian method for each element separately. After the band of the flexibility matrix of the system F has been formed, we follow the procedure described above. For each rod, we pull out the cells corresponding to the rod attachment points from the flexibility matrix and form a truncated flexibility matrix of the rod attachment. This is a relatively small matrix. In the case of a spatial system, this is a 12 by 12 matrix. We calculate its inverse matrix, the stiffness matrix of the system reduced to the nodes of the tested rod. Since the original matrix of the system is formed taking into account the unit reactions of the tested rod, we subtract from the reduced matrix the eigenstiffness matrix of the rod at the current value of the longitudinal force. Add to the reduced stiffness matrix the eigenstiffness matrix of the rod as a function of the parameter alpha. Find the eigenvalues of the alpha. For each value alpha, we are building a buckling mode. Based on the shape, we determine about which principal axis of the section the bending occurs according to the given mode. Continue searching for the eigenvalues until we find the smallest eigenvalue for each principal axis of the section. Using the formula mu equals pi L, We determine the coefficient of the buckling length of the rod relative to both principal axes of the section. This figure shows the design model for a 4-story, 4-span frame. All rods are of the same cross-section. The floors and overhead cover are loaded with the same distributed load. The graphs in figure show the curves for the buckling length coefficient mu versus the load level for columns A, B, C, calculated programmatically using the algorithm described above. The abscissa scale in these graphs represents the load level relative to the critical state. The numbers indicate the floor numbers. The table shows the limiting values of the coefficient mu corresponding to the critical state of the structure. These limiting values correspond precisely to the standard general stability calculation scheme, where, when searching for a critical state, the load increases simultaneously in all system elements proportionally to the same parameter. This figure shows the design model for a truss loaded with a uniformly distributed load along the top chord. The critical load is 16,367 Nm. Figure shows the values of the buckling length coefficients obtained from the calculation of overall stability with a proportional increase in longitudinal forces in all elements and below, obtained as a result of the calculation using the algorithm described above. Here coefficients μy, values of the buckling length coefficient for bending out of the plane of the truss, μz, for bending in the plane of the truss. Thus, the speed of the algorithm described above is ensured by the fact that, as demonstrated, the boundary conditions at both ends of each element can be obtained by inverting a very small portion of the overall flexibility matrix of the structure. As well, it is shown that to solve the problem, not the entire flexibility matrix is needed, but only that part of it that lies within the band structure of the system stiffness matrix. An effective method for generating the desired band of the flexibility matrix is proposed. Experiments show that the time required to calculate the buckling lengths of all structural elements is comparable to the time required for a single static analysis per one load case. Furthermore, the use of only the band structure of the flexibility matrix does not impose excessive demands on external memory. A few more words about testing the local stability of rods using the buckling length method. There is a debate in scientific communities about whether it is appropriate to fix the stress state of the structure at the level of the applied loads when searching for the critical value of the tested rod. Or should the forces in all elements be proportionally increased until a general loss of stability is reached, as is done in most industrial software packages? First, it should be noted that the local stability checking of rods has nothing to do with the loss of stability. As noted in the introduction, we are actually searching for the limiting value of the compressive force at which the design stress appears in one of the rod fibers. And if the force acting in the rod is below this limit, there is no danger. This limiting force is determined by the rigidity of the rod, its length, and the boundary conditions for the member. Boundary conditions are determined by the structure and its stress state. The higher the stress state of the structure, the more weakened the boundary conditions for a particular member, that leading to a lower critical parameter alpha and, consequently, to higher buckling lengths. Therefore, kilometer-long buckling lengths are obtained when we intentionally reduce the structural resistance by proportionally increasing the forces in all elements when calculating the overall stability. In order for the buckling lengths will correspond to the actual boundary conditions of the rod, it is necessary to include the actual stress state in their analysis, which is ensured by the algorithm described above.